Thank you for the introduction and for the chance to speak at this year's Embedded Vision Summit. So let's dive right in, and I want to explain why this is a very important topic and why a new approach is needed. So if you look at our industry of embedded vision devices, there's a general trend where engineers, product engineers in our field have been underestimating the capability of hackers. And we need to realize that hackers who are attacking camera devices are very skilled and way more skilled than we've been giving them credit for. This includes nation state attackers, where you see sophisticated attacks coming from nations all around the world. And it also includes private individuals who are doing it either for reasons of profit or criminal activity or just for laughs. But just in general, hackers these days are very sophisticated. There are also sophisticated tools that make it easy for people to get into the field and become very good at hacking devices. And this is a growing threat that will become even more of an issue in the future. So we as an industry, we as product engineers need to start taking this more seriously and have a new paradigm for designing security into our products, where instead of just making best effort security or security by obscurity or other approaches that just aren't good enough, instead we need to focus on architectural solutions where we actually design our product architectures in such a way that we can define certain security guarantees and then build those guarantees straight into the architecture. So before I dive into the how, first let's quickly touch on the why. So there's a growing level of distrust among consumers in camera products in general, and for good reason. Speaking as a consumer myself, I certainly have growing distrust of camera products. Internet-connected cameras in general are hacked and abused in a variety of ways that leads to real harm for people. So here are some just examples from the news. So baby monitor cameras get hacked, very frequently. And speaking as a parent myself, this is a real concern. My wife and I do not have a baby monitor camera, even though we would like to, just because of this concern. We, as someone who works in the field, I know how easy it is to hack these devices. I don't want someone to hack and spy on my baby. Security cameras. So there was this company called Verkada that got hacked, and 150,000 of their cameras were sort of broken into through this cloud management portal and exposed private video streams from Tesla factories, jails, hospitals, schools, police stations. So very, very private locations that need to be secure, but were exposed to the internet and then easily hacked into through an insecure management portal. And then finally, things have gotten so bad and distrust has, for good reason, gotten so high that even the FBI is actually warning consumers, saying that if you're not using the camera on your smart TV, you should just put black tape over it. That just the advice, and it's good advice for consumers, is if you're not using a certain camera, cover it. Because these devices are just way too easy to hack. They're not architected securely. So let's look into how we can do better. How can we as product engineers do a better job and actually define architectural guarantees that make certain types of attacks infeasible architecturally. So I'm going to walk through one proposed architecture it's an approach. It doesn't use any proprietary technology. All these ideas are very old ideas that have been around, I think, for decades. But I just want to introduce them, and I'm sure some of you have already seen some of these ideas, but I want to call attention to them because these ideas are very timely, where we need, as a field, to start taking these ideas more seriously. So let me start. I'm going to walk through, over the course of the next several slides, one architectural approach, and then also touch on some other approaches briefly. So let's walk through one example. This is the Embedded Vision Summit, after all. So what I want to emphasize is that for a lot of embedded vision devices, right, they are, by definition, running some sort of computer vision, machine learning, often neural network-based type of algorithm. And so frequently it's possible to run the algorithm of interest on potentially a convolutional neural network accelerator or on a chip, for example, like the Movidius Myriad, that can run more classical CV algorithms on it, or other types of accelerators. Generally speaking, if you look at all the companies at the summit, there are lots of companies making great chips that accelerate computer vision in an embedded context. So let's look at the simplest system. If you were just building an offline system with no connectivity at all, and you wanted to do some sort of embedded vision, this is what you would do. You'd have one or more cameras connected through a high bandwidth bus, probably MIPI CSI, to a vision processor, and that vision processor will run some algorithms. So let's say let's use the example of let's say if there's a device that is going to be in a store and it wants to count the number of people that come through the store at different times of day. So it's very simple, just looking for people and just counting people and timestamping the number of people that go through at a given time. So that's a simple algorithm, just very basic, pedestrian detection, can easily run as a neural network or classical CV algorithm on an accelerator. Okay, so now let's go into the next step of a proposed architecture here. So now what if you want to have a real-time internet dashboard where somebody can, the store manager can log in from the web, from their phone, whatever, and then see the real-time number of people coming through the store. So how would we design that system to architecturally prevent a hacker from getting access to the live video of the store? Well, that's doable. So the first thing to think about is to actually limit the bandwidth so that you can make it so there's just not enough electrical bandwidth on the buses in question to actually exfiltrate video. So if you look at what information actually needs to get from the vision processor to the internet, if you're just talking about actually counting people or many other embedded vision applications, you don't need that much bandwidth. You can use something like SPI, where it's just a much smaller bandwidth than would be used to carry live video. So as an example, I would propose that a simple thing to do is just to output JSON. So just the vision processor could, once every frame, output JSON saying, for example, in this case, it would be the number of people. It would just be a simple JSON object saying there are this many people in this frame. And the reason I suggest JSON is that you can easily do much more complicated representations of higher level concepts. So if you want to even say, for example, if it's trying to say not just the number of people, but the number of estimated men and women or people of different ages, whether people are in groups like families or walking alone, whether there's a stroller or not. If you wanted to have all these more high-level properties, or even represent their bounding boxes or information about their color, like the color of clothes people are wearing or things like that, or whether they're wearing a hat, whatever the case might be, all of that stuff could be easily represented in a flexible way in JSON. And so you can get very rich information that might be useful to the business owner or to whoever needs to use this dashboard, but you don't need the video. You don't need actual video images to ever leave the device. All that information about everything that the end customer might care about can be converted on device in the vision processor to a text or metadata format that is not image files and not image frames. And so then the way you wire that is that you can have the vision processor's output buses only be very limited bandwidth, so that even if a hacker manages to compromise your system entirely, which they will, hackers are good. You have to just assume from the start that your system will be entirely compromised. Obviously, you're software folks, and if you're a software engineer, you should do everything you can to make sure that doesn't happen, but it still will happen. But we should take software precautions, code signing and end-to-end encryption, every possible precaution, but also design the hardware to assume that the software will be fully compromised. So now let's move on. So how do you actually go about getting this data to the internet? So if we want to design this in the most secure way, here's what I want to propose as an architectural security step. So on the previous slide, we said one architectural security step is to limit the bus bandwidth so that the bus bandwidth can't carry video frames. Now, the other thing is to introduce something called a data diode, or which in this talk I'll also call a fire break, which is a dividing line in the system that data can only cross in one direction. So how will we do that, and why would we do that? So here you see I have a gap in this line. You see the arrow is blue, and then there's a gap, and then it's red. I'm going to explain what that gap means. And so, but in terms of where it is and why it's there, we want to establish a one-way flow of data from the vision processor to the application processor. And I'll jump into why. So we want to establish something that is traditionally called a data diode, or in this application, I'm going to call a fire break. And it's a kind of wiring scheme that establishes a dividing barrier, a dividing line in your system where data can only flow one way. And so why would you do that? So basically, and the reason I'm calling it a fire break is that it's dividing between a quote hot side of your system and a cold side of your system. And the reason I'm calling one side the hot side is that it is much more likely to be hacked more often. Again, we need, on the software side, every precaution needs to be taken to prevent hacking, but also we need to accept that hacking will happen sometimes because hackers are really good. And there are a multitude of approaches to do hacking, including insider threats. Somebody who works at your company could just steal your key, a disgruntled employee, social engineering attacks. There are all kinds of ways for people to get access into systems. So that's why having this electrical architecture approach to security as well is really important. So the application processor should be protected through every possible software measure, including code signing, and having a bug bounty program, having third-party consultants review your security and try to attack your security and find weaknesses so you can fix them. You need to deploy software patches on a regular basis and deploy them as quickly as possible, because hackers will typically wait until new vulnerabilities are announced and then immediately try to use those vulnerabilities before the patches are deployed. So you need to get patches out ideally 1 or 2 days after the vulnerability is announced, not weeks, not months, but days or 1 day. And all of that stuff is very important. But even with all that stuff, the side that we're calling the hot side of the system will still get hacked sometimes. So the cold side, and the idea with this fire break or data diode is to protect the cold side. So it's actually electrically impossible for the cold side to be hacked. So how do you do that? And the way you do that is to actually make it so data can only flow one way. So you want to wire things so that data can only flow from the vision processor to the application processor, but cannot go the other way. So if you want to read about this in just publicly available literature, just look for the term data diode. So it's a common term, and it's used. One application where it's used a lot that's very important is industrial control systems. So if you have, this is a common application for IoT. Let's say if there's an oil pipeline and there have to be some sensors on it to sense pipeline pressure, temperature, strain and stress on the pipes, et cetera. There might need to be IoT sensors that sense those kind of things and report them to a distant location. But you certainly don't want those sensors to be hacked, especially if they're connected to valve, especially if they also control valves, some sort of industrial control loop, et cetera. It's really bad if those things get hacked. If they do, they could be used for terrorism and causing explosions and fires. So it's really bad if they get hacked. So that's where data diodes are applied, which is that you can have a one-way either wiring scheme or a fiber optic scheme to where basically you have a kind of a link of some sort. It could either be a fiber optic fiber cable, or it could be a wire. And then you have one side that only has a transmitter component and not a receiver, and the other side that only has a receiver, and that's it. So then that way, there's simply only one way that things can actually flow. One side only has a transmitter. The other side only has a receiver. So when this is implemented in an industrial context, it's commonly done with fiber optics. So one side will have, a laser, and that's it. And the other side will have a, photodiode or whatever, and that's it. In an embedded context, we don't typically use fiber links. So instead, we're going to talk about wires or, PCB traces. And it's pretty simple in the case of, if you're, as shown in this example, if you're talking about a SPI bus, for example, then what you do is, first of all, you should, on the sending side, on the cold side, you should use an output only pin. So you want to have, and the reason I suggested SPI and not I2C, for example, is that I2C fundamentally requires information and bits to flow in both directions for the protocol to work. Whereas SPI, you can wire up one-way SPI with no acknowledgements or anything, just purely one way. And that's what you want here. So you want to have the sending side, generate the clock, send, but just no acknowledgements at all, just a blind send. So I2C would not work here because any sort of two-way interactive traffic, protocol, acknowledgements, anything like that, even a clear to send or ready to send, et cetera, all those things are not allowed. That would violate the whole point of this data diode if I were break. It needs to be complete one-way blind send. So I want to emphasize this rule needs to be strictly followed, no exceptions. So that means, you might think, oh, I'll make an exception for JTAG, whatever. Or I'll use I2C because I want to use I2C and that's easy. This really needs to be strictly followed. Hackers are good. If there is even the slightest vulnerability in your system, people will find out how to exploit it. You might not think that people care about hacking your product, but the fact is that hackers typically, for one thing, not all hacks become publicly known. So sometimes hacks will target a particular individual. This one case where this happens a lot is the targeting of journalists. So, nations that are crack down on dissidents and crack down on journalists sometimes will hack your devices, and you won't know it because it's not publicly targeting millions of people, but it might be targeting one or two people who are journalists, and as part of a crackdown that might even lead to those people eventually losing their lives, or at least ending up in jail. That's one example. There also, just in general, devices can be hacked targeting specific ethnic groups. So, for example, in the news 1 or 2 years ago, it was discovered that China had done very specific attacks against people from the Uyghur minority, where it was using zero-day exploits targeting iPhone devices, and I think using 5 zero-day exploits all at the same time. So very expensive exploits, and these exploits were worth millions of dollars, but were not used against people in general. They were only targeted at very specific people of a certain ethnicity in a certain province or part of China. So just because you don't think your device will be targeted, or maybe there's no incentive for people to target en masse, doesn't mean it won't be targeted for specific people or ethnicity or some other specific targeted reason. So everyone needs to be careful because if we're all making products with cameras, we all have to be responsible. If these things get hacked, they can threaten people's safety, and that's really important. And we got to take our jobs seriously. So no exceptions. People are skilled. People spend millions of dollars developing these hacks. Nation states employ like the best and the brightest. Right? You have nations where you have millions of smart people, and then hundreds of thousands, or at least tens of thousands of people that are working every day on trying to crack into the best secured systems and still finding ways in. So we need to anticipate the hackers are really good. So no exceptions. No JTAG, I2C, anything two-way, out of the question. For a data diode to be implemented and to actually be a true data diode, it needs to be literally one side can electrically only have output pins and the other side can only have input pins. And if you're not sure, or if your chip doesn't have dedicated output only pins or input only pins, just put an actual buffer component. So just, find a cheap couple cent buffer, and then you can be sure. That's the best way to be secure. If you're not sure about the capability of the pins on either side, it takes almost no board space. You can get a little 4-pin tiny chip, like a square millimeter or something. And then for sure. Then you have a buffer, and then information can only flow one way. Okay, so let's dive into some questions. So one important question. So let's say you have everything really strictly through a buffer or something, truly enforced data diode. So how do you update the firmware on the cold side, on the send-only side? So the way I would propose to do that is to require physical access to the device. So as an example, this could be through USB. So the firmware update process should require, in order to be secure, it should require physical access to the device. And that's the gold standard in security, where if an attacker gets physical access to the device, already all bets are off, because they could, if they have physical access, they could literally just swap out the circuit boards entirely, or just swap out the whole device with the device that they built. And this does happen sometimes. So people do actually, for example, intercept devices while they're being shipped and either swap things out or make changes to the hardware. So in the cases of high, well-funded attacks, that does happen. But basically, if someone has physical access to the device, all bets are already off. So that's a good kind of rule of thumb for what's the right approach for updating the firmware. So one way this could be done is that, let's say if your product uses USB for charging, you could have it so that the USB data lines are wired into the cold side and only the cold side, not the hot side, because you don't want a connection to exist between them. But only to the cold side, and then you could also require confirmation. So for example, maybe the user has to press the reset button while charging in order to trigger a cold side firmware update. And the reason you want that confirmation is you don't want it to be able to update every time it's charging, because then the hacker could just, if the person's charging with a PC as the charge host, then the hacker would just hack the PC and then from there hack into your device. So that would in that case, then anytime you're charging, the device is vulnerable. So you don't want that. You want the user to have to actually confirm an update with, for example, a reset button press while charging or something like that. For the hot side firmware, that can just be updated through standard over-the-air updates, like I'm sure we're all used to at the summit, over Wi-Fi, Bluetooth, et cetera. Obviously, you want code signing, and you want that for both firmware sides. So for the hot side firmware and the cold side firmware, everything should be code signing, strong encryption, et cetera. The goal here is what's called in security defense in depth, where you have multiple layers of security so that if some layers are broken through, that there are still layers remaining. And we're aiming here to add this new layer of basically hardware architecture enforced security. Okay. Now, another challenge is that some applications, may either be perceived to require outputting live video or may actually require outputting live video. So it's there is I guess I'll say that not every application will be a fit for the techniques I proposed, but many are. And it's an area where, part of our job is to be creative. So there are a lot of applications where it might seem like live video is required, but actually it's not. So I've spoken about the example of a device that counts the number of shoppers in the store. Another example that I would say is a little bit more cutting edge, but is possible, is in a baby monitor example. Currently, baby monitors actually stream video, but there have been research papers where researchers have come up with vision algorithms that basically, through a camera, detect key metrics such as even the baby's heart rate purely through a camera. So heart rate, breathing rate, those kinds of things can be detected. And so in the future, when these algorithms are better and are medical grade, you could have baby monitors where they don't actually stream out the live video of the baby, but they just stream out the metadata of heart rate, breathing rate, and then that way they can sound an alarm if those rates get to unsafe levels. So I would just encourage you all to think creatively, because we may think that live video is required in many applications, but often it's not. And then often also maybe video is required for archival reasons, but not live. So in the case of a security camera, you can have just a ring buffer, like a rolling buffer of a security camera recording video to disk, so that way you can transmit the metadata live. And then if there's a concerning event, then somebody can plug into the disk or access the data archivally. For example, if it's a security camera, that it could be used for archival purposes during a crime investigation of a burglary, whatever the case might be. So basically, storing video archivally is certainly an approach to consider. Broadly speaking, use your creativity, right? We're here to innovate. So this is an important area for innovation: is how can we make our systems secure? How can we design systems to not have to transmit live video and instead only transmit metadata? Because ultimately, the less data we transmit and the more that we put architectural barriers to prevent data from escaping or being hacked, then that helps our customers. Security is really important and becoming more important because hackers are becoming more skilled and more creative. So we have to get creative on our side too. Okay, finally, I'll address the question of cost. So I proposed having a separate dedicated vision processor, which for certain applications might seem to be too expensive. So I will address some other ideas for how the cost can be kept down. So one approach that if you're in a low cost industry where maybe you have very small margins or something like that, and you need to really keep the cost down, then one thing you could think about is in certain cases, maybe your camera module, you can actually use something like the Qualcomm Glance, which is a camera module with a very simple built-in vision accelerator in the module. So if your compute needs are low, and if the field of view and everything from the module matches your requirements, you could use a module like that. You still need a microcontroller to host the firmware for for the glance camera module, but that could be any really cheap microcontroller. All it has to do is load in some basic settings and a couple of kilobytes of data into the glance module. And then now you can still establish this data diode or fire break in between that microcontroller and your main application processor. Or in certain applications, you might be able to have a data diode or fire break in between your application processor and your radio. So if you have a radio that's standalone and can self-host its own firmware, for example, like the Espressif ESP32, then you can actually have a one-way write-only connection from your application processor to your radio. And again, you need to be very strict about the wiring. So seriously, no exceptions. You really need to have it so that information is literally flowing only one way. When in doubt, put buffer components. Make it so that you're sure that information can electrically literally only flow one way. That includes clocks, that includes interrupts, everything, only one way. But basically be creative. Think about if you think about where to put the fire break, then there might be a certain option for your system that has the lowest implementation cost. So I've presented a couple options. You can put it between the camera module and the AP, or between a vision processor and the AP, or between the AP and the radio. So there are some different options, and you can see which one's best for your application. Okay, so I'll quickly summarize because I think we're at time. So, attackers are really good. If something can be hacked, it will be hacked. Of course, you and your software engineers need to take every possible precaution, and need to use code signing, strong encryption, have a bug bounty program, have red teaming, have basically every single best practice to keep your software secure. But even then, it will still get hacked. So then on the electrical side, it's our responsibility to take these threats seriously and assume and understand that attackers are very competent. So we need to be creative and be willing to put a little bit more cost in our devices in some cases. But there are ways to do this that do not add very much cost. And it really is important, because at the end of the day, this can protect journalists and dissidents from governments that are not democratic. It can protect everyday people from cyber criminals. It can protect against a wide variety of threats, and it's really important. And like I said at the start of the talk, even the FBI is recommending consumers to put black tape over their cameras that they're not using. So this is a bad perception for our industry. People don't trust our devices for good reason, because our devices get hacked a lot. So we need to take this more seriously. We need to be creative, and we need to put security as a priority and think about ways such as the data diode concept that can actually build security guarantees into our system. So this part of the system is the cold side. It will never be accessed from the internet. Information can only flow one way out of the cold side, but not in. So thank you very much for listening to this talk. I hope that you're able to take some of these ideas to heart and tell your colleagues about them. My company doesn't make any money off these concepts or anything like that. These are concepts that have been in the public domain for a long time. I'm just trying to spread the word because these concepts are important, and I hope that they'll get broader recognition and adoption. So hopefully you all can spread the word to your colleagues as well, and just try to popularize these concepts. And we as an industry can do better. We can stop relying on software security and have both software security and hardware architectural security. We can innovate. We can find new architectures. What I propose is probably not the best. There will be better concepts that people will come up with that are even better than this, or that build on top of this. So let's be creative. Let's be responsible. Let's take this all to heart. For further reading, you can look at these links. You can email me if you like at jon@neurobinder.com, and I'm happy to answer any questions. And thank you so much. Thank you for taking this seriously and for caring about your customers and their privacy and their security. Really appreciate your interest, and thank you very much.